Let's talk about absolute versus conditional convergence. So let's start with an example. Here's a series where the terms are all reciprocal squares, but it's got an unusual pattern of minus signs. So it's not alternating, which is unfortunate because if it were, we could apply our ideas of alternating series. Those are very powerful. And we've seen that they tend to converge much more often than non-alternating series. If you want to pause the video, you might want to figure out the pattern of the minus signs. You might be able to get it. What I decided to do was it's minus if this is a square of a prime, and plus if it's a square of a composite number. And so that's going to be a fairly irregular pattern of pluses and minuses, definitely not alternating. The question is, of course, does this converge? If you want to look at the partial sums, 1, 1 minus a fourth, 1 minus a ninth, I've just sort of sketched it roughly here. It starts out with 1, then goes down, then goes up because the plus 1/16 goes down, goes up, kind of wiggles a little bit. But because these numbers are getting smaller, the wiggles die out. And so it certainly looks, I would say, like it is trying to converge to some limit. And so that would say the series would converge. Well, here's what we can do. We can think about what would happen. We had a hint from the alternating series is that alternation of plus or minus signs really helps converge and certainly doesn't hurt. This isn't strict alternation, but the idea here, the slogan, is basically that sign cancellations, any kind of sign cancellations, putting in minus signs, they never hurt you. That never hurts. Let's see, plural. Yeah, never hurt. Okay. So this is kind of a slogan here. And what I'm going to do is I'm going to compare this. I'm going to say, well, what if I had 1 plus 1/4 plus 1/9 plus 1/16 without any of the signs? Okay. So that would be something where the partial sums would go 1 and then go up, 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 up. But we know this one converges. This is a p-series. This is the sum of 1 over n squared. And that 2 is bigger than 1, so that converges. And again, our slogan, this is not very precise, not intended to be. Our slogan is that these terms go to 0 fast enough so that when you add them up, it doesn't run away to infinity. And now what I'm doing here is I'm changing some of the signs so that I'm going to get some cancellations. So the contribution here partly cancels out. That just makes something smaller. This partly cancels out. That makes something smaller. This partly cancels out. And even though it doesn't alternate completely, like here I get 2 pluses in a row, I'm going to get a lot of sign cancellations. So compared to this, basically I'm adding up smaller stuff. Now, that's intentionally vague, but it's the right idea. And here's the terminology for this. So here, like the a sub n was plus or minus 1 over n squared, and that was minus if n is prime. Well, the absolute value of the terms is just 1 over n squared. And what I did when I looked at that other series was I was comparing it, I was looking at the sum of the absolute values. So what we do is we say if I have a summation, and if the sum of the absolute values actually converges. And the idea, we'll make this precise in a second, the idea is that that could only hurt you. Suppose you take away the good effect of partial sign cancellations, and it still converges. Then we say that the original sum converges absolutely. And that should sound like a better version of convergence, because in fact, to say it converges absolutely, it does also imply that it just converges in the usual way. And that's the first big theorem here. And that's the precise version of throwing out minus signs can't hurt you. Throwing out minus signs, putting me back in the minus signs can't hurt you. That's what I really should say. The one with the plus signs, if that's good, like this guy, if you know that's good, like an example, then the claim is, and I think I'll do a separate video for the proof of this. It's not hard, but we never really need the techniques from that proof. If this guy converges, then putting in some minus signs and having some of those cancellations happen only makes it more likely to converge. And remember, we've seen that in the most special case already, big time, with alternating series. And there, a lot of the times you get things that converge, even if the one without the minus signs didn't converge. And we'll have a terminology for that as well. So one thing really right now is that I'm not taking the absolute value of the sum. This is the sum of the absolute values. That's really important. That I'm flipping all the individual signs to plus and preventing any cancellations. I'm not just taking absolute value of the answer. That wouldn't be that interesting. That would just be, well, if it already converges, let's just throw out a minus sign it might have. So again, mainly just focusing on the terminology here, not so much on the proofs. But let's say the first big theorem is, as suggested by the terminology, if a series converges absolutely, then it actually converges. It does, just plain converge. And that's the precise theorem stating, with this terminology, stating that if throwing out the minus signs gives you something that still converges, then boy, the thing with the minus signs is going to be at least as good. So here's one more notation. There are going to be plenty of series, like many alternating series, where if you throw out the minus signs, that's exactly what was making it converge, and it will no longer converge. So if a series converges, but not absolutely, we say it converges conditionally. So conditioned on the minus signs being in there. So the world's most classic example of that is the alternating harmonic series. That's an alternating series. So here the pattern of minus signs is a pattern that we understand and we've proved is particularly good and really helps something converge. It's an alternating series with the sizes of the terms going to 0, and uniformly and monotonically to 0. And so this converges. But the reason it converges is because of the minus signs. If you didn't have the minus signs, and so this is exactly the different modified series that you would create to test for absolute convergence, you get the harmonic, and that's famously not convergent. So this is the one you always want to go back to as the simplest example, the most famous example of a conditionally convergent sequence. Okay, so one reason we're doing this is that we have tools, the comparison test, integral test, stuff like that, and the new test we're going to get in a second, ratio test and root test, all apply to essentially work on sizes and not on signs, and so they aren't tests that really can detect the good effect of plus or minus signs. And so they're really going to be tests for absolute convergence. We're going to take a series and essentially throw out all the minus signs that it has. And if we're lucky, those minus signs weren't the reason it was converging, and we're going to be able to say, oh, it converges absolutely, therefore, oh boy, yeah, it certainly does converge. It's much more subtle to have tests that actually say, oh, this converges, but because of the minus signs were really necessary, and that's the conditional. We do have a case with the alternating series test where we can totally see that. And so that's the most famous example. But when the signs are more subtle in a kind of a weird pattern, like with the prime example, that can be more tricky. So yeah, I think I'll do another short video with a couple of the proofs of some of these statements. And then we'll get into ratio and root, which is back in the line of, hey, let's have some tests for convergence.